All right, my name is Bigy Ambat, and today I'll be talking about recycling greenhouse gases with titanium and boron. And I'm representing the Harman Research Group for this research project. So just a little bit of a background before we start going into the details of our research. I just wanted to give a quick introduction about the industrial chemical cycle. Oftentimes, our industrial chemical cycle that we have today is very inefficient and unsustainable. And the main reason is that we produce a lot of energy and a lot of waste products as a result of our synthesis. And if you look at our reaction cycle specifically, we have our feedstocks, which are our chemical building blocks of our general industrial synthesis. And so those feedstocks are often derived from fossil fuel extractions. And the bulk synthesis of our chemicals requires a large amount of energy. And the energy production indirectly produces greenhouse gases as a result. And so the main aim of our research project is actually to take those environmental waste products and recycle them into renewable feedstocks. So essentially converting gases like CO2 or methane into more feedstocks, like, for example, formic acid. And those feedstocks can be used to create chemicals in our chemical industry. So just a quick background about converting those environmental waste products into our feedstocks. One method of doing that is small molecule activation. And so using small molecule activation, we can recycle these common molecules into usable derivatives. So for example, carbon dioxide into formic acid or nitrogen gas into ammonium. And by doing so, we can close the loop of chemical production. And essentially, we're taking our byproducts of our chemical production synthesis and turning them back into our reactants. But the main challenge associated with these small molecule activation reactions is that they are not energetically favorable. And that's primarily because those small molecules are very stable inherently. And so it takes a lot of energy to convert them into the products that we want to. And so to perform these small molecule activations in a feasible manner, we need a catalyst. So a great example of a catalyst that we've been using is diboroanthracene. And it's been an established molecule for small molecule activation in our lab. And that the way that this works specifically is we use electrochemical input, essentially a electric current, to activate our DBA complex. And using this DBA complex, we can perform and catalyze some of these small molecule reactions. So the unique characteristic of our DBA molecule specifically is that it has these 1 electron reduction at mild reduction potentials. And so having this specific quality makes DBA a very good platform for performing these small molecule reactions. So our previous work in our Harman Research Lab, we've been able to generate this gold DBA complex called B2P2 gold. And if you look at this complex, we have about 3 different parts to it. So we have our DBA molecule that's laying flat on in the complex, and we have 2 phosphine arms that are essentially stabilizing this metal center in the middle. So we have the DBA complex, the phosphine ligand arms, and we have our metal center. So in this complex, we have our ligand arms that stabilize the metal center using sigma donation. So for example, by donating electrons directly into the metal. And using this DBA gold complex, we've been able to generate a stable oride, which was one of the first ever stable orides discovered in solution. And this molecule itself has been demonstrated to perform small molecule reactions and has been shown in our research to demonstrate that. So having established our B2P2 gold complex, the main research goal of this project was to expand upon it and create a complex using an early transition metal instead of gold. And the reason we want to use early transition metals specifically is because they are much cheaper and they are much more abundant compared to gold. And specifically titanium-2 and zirconium-2, they have been demonstrated to have catalytic uses in other research, but they haven't been observed directly in solution before. And so our research was to combine these two aims to create our early transition metal complex. So, but the main problem with our complex is titanium, those early transition metals specifically, tend to be more electropositive compared to gold. And what that means is essentially we need stronger electron donation from those ligands to stabilize the metal inside this complex. And so our plan is to use nitrogen arms for stronger donation instead of phosphine arms. So here's our general synthetic plan that we have developed to accomplish this task. We have our DBA molecule on the left, and combining that DBA molecule with a lithiated ligand, we can attach it to DBA to create our B2N2 molecule. And from there, we can use a titanium salt to insert our titanium into the DBA molecule to create the DBA complex. So we actually came up with two possible ligands that could be attached to DBA. So our first ligand is this Tritonal Phosphatomy. So we start with bromotoluene group, and we use a Grignard reagent to create a tritoluphosphine. And we keep that reaction to the side. After that, we use bromoaniline, and we use our tritoluphosphine that we just synthesized, along with triethylamine as a base to create our tritoluphosphanoamine. Here we have our 1,3-dimethylimidazolidinamine, which is our second ligand. So for this reaction scheme, we start with our imidazolidinone. We add POCl3 and a KPF6 salt. And that produces a KPF6 salt molecule. Based on that, we add lithium HMDS and 2-bromoaniline to create our second ligand. So for the current status of our research, both of our ligands have been successfully synthesized. Here we have our first ligand, our tritoluphosphanoamine. You can see from the aromatic regions around 6 through 7, our peaks integrate properly. And specifically our tolu groups, the methyl groups specifically on the tolules, also integrate properly as well at 2.38. And here's our second ligand. And here we can also see a very similar process. We have our aromatic groups that also integrate properly, and we have our methyl groups attached to the nitrogens that also show peaks at 3.3 and 2.6. So having synthesized our ligands, our plan that we are continuing to implement is to attach these imidazolidinone ligands and our phosphine ligands to DBA. And once these ligands have been successfully attached to our DBA, we plan to complex it with a titanium salt. And from here, we will add the titanium into our DBA to create our B2N2 titanium complex. And having generated this complex, we plan to perform a chemical redox on our B2N2 complex and characterize the specific bonding structure and like the bonding patterns of it. And this will be primarily done using NMR, EPR, and crystallography techniques. So having generated and created our B2N2 titanium complex, finally, we plan to perform these small molecule reaction activations using N2 and hydrogen gas to eventually convert those products into feedstocks. And with that, I'd like to acknowledge members of our Harman Research Group who are here today. And I'd like to especially thank Dr. Hill Harman for his excellent work and feedback on my project, and excellent work and help throughout our research. And I would also like to thank the undergraduate research mini grant for providing the funding for this project. And here are my references slide, and I would like to say thank you, and that's the end of my presentation.
Thank you, Bigy. Do we have questions from the audience?